While we have this rule known as the octet rule, it doesn't govern everything. It just so happens that that's a common number of electrons that an atom wants to see in its outer shell. There are plenty of examples that are exceptions to the octet rule, and that's what we're going to focus on in this video. The first kind of exception that we're going to see is when we have an odd number of electrons. This will mean there will be an unpaired electron. An example of such a compound would be NO. Okay? We would start with the same basic steps of drawing a Lewis structure, counting the total number of electrons. Nitrogen brings 5 valence electrons. Oxygen brings 6 valence electrons. So total, I have 11 valence electrons to work with. So I build a framework, NO. I've used 2 of those valence electrons in bonding. I'm left with 9 valence electrons to place as lone pairs. I would start placing those lone pairs on the least electronegative atom first. So 2, 4, 6, 8, 9. I'm going to check my octet. Oxygen has 2, 4, 6, 8 electrons. Nitrogen has 2, 4, 5 electrons. So that's not very good. Can we make it any better? Well, we can imagine donating electrons from the oxygen or removing those electrons, which gives me this structure. Let's be consistent here and do it that way. So oxygen, 2, 4, 6, 8 electrons still. That's good. Now nitrogen has 2, 4, 6, 7 electrons. That's better. Can we do any better than 7 electrons? Well, if we add more electrons into nitrogen by the same method we did before, we're going to end up having how many electrons around nitrogen? We would end up with 9 electrons. And that is no good because we exceed the octet, and we cannot exceed the octet for second period elements. Okay? So this is pretty much as good as it's going to get for us. We have an odd number of electrons to start, 11, so we aren't going to be able to pair up all of those electrons. And so this is an example of what we call a radical. And a radical is an unpaired electron. So this will be a type of exception to the octet rule. I almost forgot to add that we need to check our formal charge. So we know that oxygen comes with 6 electrons, and we're going to subtract the number of bonds, so that's 2, plus electrons in pairs, so that's 4, so my formal charge is 0 on oxygen. Then nitrogen, the formal charge would be equal to 5, its period number, its group number, or the number of valence electrons that it brings, and it sees 2 bonds and 3 electrons. So that formal charge is also 0. So even though we have fewer than 8 electrons, we can still have a neutral atom. And now we are officially done with drawing this Lewis structure. Similar to the radical species that we just looked at, we can have other exceptions to the octet where there is an incomplete octet of electrons. And this is going to be true for group 3 atoms. So elements like boron, aluminum, etc. commonly have fewer than 8 electrons. So take, for example, the simplest compound of boron. It's borane, BH3. We can draw the Lewis structure for this. We don't even have to count electrons. We probably should, so let's do that. Boron brings 3 valence electrons. Hydrogen brings 1, but there are 3 of them, so that's 3 valence electrons. So we're left with 6 valence electrons to add to our structure. We build our framework. Boron in the central atom, it's the least electronegative. We are going to add our hydrogens. It can only be an outer atom, so it has to be that way. We've used 6 electrons, so we're left with 0 electrons. That means there will be no lone pairs here. If we look at my octets, for boron, 2, 4, 6 valence electrons. It's deficient. We can't do anything more, though, because we don't have any more electrons to work with. Hydrogen can only have a duet, because it's in group 1. It can only have that 2 electrons in its valence shell. So this is as good as it gets. This is an excellent representation of borane. And it also explains, in part, its reactivity. So borane is very reactive with water. In fact, it's explosively reactive. A lot of heat is released upon mixture with water. And the reason being is because having fewer than 6 electrons, it's highly unstable and highly reactive. So we actually form this borane complex with water where boron gets an octet and a formal negative charge. So we form this borane water complex that now all of my atoms have an octet, albeit we do have formal charges, but that is secondary to satisfying the octet rule. So we've explained the reactivity as it results from the structure. Okay? So why don't you try this next example? The last exception to the octet rule that we're going to see is for atoms having an expanded octet. Atoms having more than 8 electrons in their valence shell are known as hypervalent. And as a rule, these hypervalent atoms must be in period 3 or below. So we're talking the third row of the periodic table and lower. An example of a hypervalent atom would be in this structure of PCl5. So we follow the same rules for drawing Lewis structures, counting my valence electrons. So phosphorus brings 5 valence electrons. Chlorine brings 7 valence electrons. There are 5 of them, so that's 35 electrons. So total, we're working with 40 electrons. We build our framework with the least electronegative element in the center. We use some intuition here a little bit too, because there's really only one way that these atoms can combine, and that is with one central atom. So I've used this framework where I've used 2, 4, 6, 8, 10 electrons. So I'm going to subtract those out. I'm left with 30 electrons that I'd place as pairs, starting with the outer atoms first. So 2, 4, 6, plus 6 more is 12, 6 more is 18, 6 more is 24, plus 6 more is 30. I'm finished. So now I can check the octet for my atoms. All the chlorine atoms have 1 bond and 3 lone pairs, so they will have an octet of electrons. And then when it comes to phosphorus, 2, 4, 6, 8, 10, yikes, doesn't obey the octet rule. But we'd have to check and say, well, is phosphorus in period 3 or below? Well, yes, it is in period 3, so it is sufficiently large enough to accommodate more atoms around it and can exceed the octet. We've already discussed that period 2 elements could not exceed the octet. So something like NCl5, the derivative of the phosphorus pentachloride that we looked at a minute ago, would not exist because nitrogen cannot exceed the octet of electrons. Now, if we look at some other data and we look at this series of compounds where the halogen varies as attached to the phosphorus atom, we'll find that there is a decreasing stability. These become less stable as we go up the list here. And in fact, phosphorus pentaiodide does not exist. It is too unstable. Those iodine atoms are too large to fit 5 of them around one central atom. So typically we'll see atoms being small and electronegative attached to elements that are going to exceed the octet in this way. So another example would be SF4. If we draw the Lewis structure here, we get this arrangement of atoms. And taking a step backwards and counting electrons, sulfur brings 6, fluorine brings 7 times 4, so 28. We have 34 electrons. Minus 2, 4, 6, 8 in bonding, I have 26 electrons left. I'd place 24 of them in pairs on fluorines. So there are 2 electrons in the 3 pairs, so that is 24, gives me 2, and those last 2 would be placed on the central atom. So now we can see that the fluorine atoms all have satisfied the octet. They are happy and pleased. The sulfur atom has 2, 4, 6, 8, 10 electrons, and that's completely fine because sulfur is in the third period. It can have an excess of 8 electrons. And sometimes we'll even see up to 12 electrons around a sulfur atom. To summarize, there are 3 exceptions to the octet rule that we're going to come across in this course. One is when we have an odd number of electrons, and this will result in a radical species, which is an unpaired electron, and that atom will have fewer than 8 electrons. It's relatively rare to have these free radicals. Then the second is having fewer than 8 electrons, which is common for group 3. So boron and aluminum will typically have only 6 valence electrons in their neutral state. And this is also relatively rare. Now, more common though is the third exception to the octet rule, and that is having these expanded octets. And expanded octets can only happen for atoms in period 3 or below, so they have to be sufficiently large and have those d orbitals accessible to hold electrons. And in general, the atoms that are attached to those are small and electronegative. So we can fit an increasing number of atoms around those central atoms. If you have any questions about expanded octets or any of the other exceptions to the octet rule, please let me know. Thanks for watching.